Alright everyone, welcome to another Physics QBits video. In this QBit, I'm going to be sharing my patent-pretending four-step process for basically solving any kind of force problem. I really like having this procedure, or just generally procedures like this, just so that when you run into a problem and you're not sure what to do, this is kind of a good general way to get started. And this is kind of the process that I've settled on as a really great way to solve most force problems. So let's go ahead and get started. All right, so first, I want to say a couple things about force problems in general, right? The general structure of a force problem is we have some object sitting in some situation and there's a bunch of forces happening to it. And the idea is to use Newton's second law to understand how those forces are going to influence that object. So Newton's second law mathematically says that if I have a bunch of forces, Fi's, and they're all acting on the same object, then the sum of those forces is going to be what we call the net force. And the idea is that Newton's second law tells us that whatever kind of total action the forces have on some object, right, the net force is going to be related to the overall push or pull that that object experiences in the form of the object's acceleration, right? So adding up all the forces on the object tells us how that object accelerates. Good. And so the general structure of like solving a force problem looks like drawing a free body diagram, just so that we kind of understand what all the forces acting on something are, right? Then once we draw the free body diagram, the goal is to use that to write out some Newton's second law equations. So specifically now we can actually add up all those vectors, right? And then we can solve for the acceleration. We'll say solve for something interesting, because sometimes, right, you get the acceleration and you have to solve for one of the forces or something like that. And because of the nature of vectors, right, because these are, all these forces are vectors and the acceleration is a vector, then we also know Newton's second law really holds in both the x and y directions independently. So in other words, my kind of full set of Newton's second law equations generally is helpful to write out like this. F net in the x direction equals m times a in the x direction, right? And F net in the y direction is ma in the y direction. So in other words, the total forces in the x direction tell me about the total acceleration in the x direction, and the total forces in the y direction will tell me about the total acceleration in the y direction. These two coordinates kind of don't really have anything to do with each other, right? X and y are independent, and so you can really generally set up equations for kind of each coordinate independently. Okay, with that in mind, let's move on to the actual process itself. So my four-step process starts with the following. The first thing we always do in a force problem should be to draw a free body diagram. The reason is because, right, when we need to sum all the forces, and I'm going to write Newton's second law one more time just up here. Fi equals F net equals ma, right? When we draw the free body diagram, the goal is to make sure we're properly accounting for all these individual forces so that we can accurately compute the net force, right? If we are missing a force or have extra forces on our free body diagram, that's a problem, right? Because now the free body diagram and our idea of what forces are acting on this object no longer reflect reality. And so that's going to give us some problems down the line. We'll have some equations that probably won't make sense, right? So to do this correctly, we really want to draw a free body diagram. If you tend to struggle with drawing free body diagrams or just have trouble starting, or like you make a lot of mistakes or something like that, you can check out the video I've linked in the description. I have a little procedure for what you can do to kind of eliminate mistakes in your free body diagram and make sure that you're careful about which forces end up on the diagram itself. Okay, the next step is going to be using the free body diagram to construct our Newton's second law equations. And so one thing that can happen is you can draw your free body diagram, and your free body diagram can be totally correct, but if you're not exactly sure what the connection between this diagram and the actual equations are, then you can get into some hot water, right? And so there's kind of one general piece of advice I have here. If it ain't on the free body diagram, It ain't in the equations. Basically, you should stare at the free body diagram and use the forces that you've chosen to represent there in order to decide what the Newton's second law equations look like, right? And we'll see kind of an example of that when we do our practice problem. Okay, great. Now, the third step is what I think is kind of the hardest one in the process, and that's what I call the thinking about the constraints in the problem. So this can be really difficult because constraints in physics can be pretty much anything, right? Some common constraints you might have run into are like something starting at rest. Technically speaking, something traveling in uniform circular motion is also a constraint. Another common constraint is when you have objects that are kind of stuck together, right? And if they're stuck together, then the acceleration of one object has to be the same as the acceleration of the other object. So we can say something like objects having same acceleration. Another constraint is like rolling without slipping. Basically, a constraint is anything that you know kind of from the problem setup about the system that you can write down mathematically, right? For example, we know that starting at rest means that the total acceleration is just 0. We know that if something is undergoing uniform circular motion, we know that the acceleration must be v squared over r, where v is the velocity of the object traveling in a circle and r is the radius, right? If objects have the same acceleration, then we know whatever a1 is has to be the same as a2, assuming we've indexed our objects like this. And rolling without slipping can be expressed as the idea that the velocity of the center of mass, or the translational velocity, is exactly equal to the rotational velocity times the radius of the object that's rolling, right? So basically, constraints are like ways that we can relate two variables that we, for some reason, know when we look at the problem. And so once we have all of these things, right, you should just be able to solve for whatever thing you're looking for, right, if you've done all these steps correctly. All right, so let's practice using this procedure on an example problem. So for this problem, I've set it up so that there's two blocks that are attached by a rope. One of the blocks has a mass of 2m, and the other block has a mass of m. And we've got our physics teacher pulling on the right-hand side block with a rope such that there's some applied force Fa. And somehow this force is causing this whole kind of contraption to accelerate to the right at a rate of a, okay? Our goal is going to be to use our force problem solving capabilities to figure out what the applied force Fa is. And so what we do know is that we know that there's some observed acceleration, and we want to find out what the applied force that is producing that acceleration is, right? A couple other things I need to mention really quick. Let's say that this whole thing is frictionless to make things a little easier. And I'm going to write that the string in between the two blocks, this one here, is massless. Okay, this will make things a little bit easier when we go on to solve the problem down here in the bottom part. Okay, so let's start by writing out our kind of four-step process. I'm going to do it here. It's going to be kind of crunched, but it'll leave us more room for problem solving. So first, we need to draw our free body diagram. Secondly, we need to write our Newton's second law equations by translating our free body diagrams into math, right? Third, we need to quantify our constraints, so things that we know about the problem. And fourth, we need to solve algebraically, right? If we've done our jobs correctly, steps 1, 2, and 3 should give us a set of equations that is just solvable for. Okay, so let's go ahead and get started and try to draw some free body diagrams, right? So for the left-hand side, the left-hand block, excuse me, I can take a look really quick and use my free body diagram drawing skills and figure out that there's one contact force from the floor, there's one contact force from the rope, and we know that this thing, well, we can assume this thing is on Earth in a classroom, right, or whatever, and so we know we have our one non-contact force. So we should expect a total of, count them, 3 forces for the free body diagram on the left. And so let's start by adding our non-contact force. This is going to be the gravitational force on the 2m block. And I'm just going to go ahead and shortcut this. We know that the gravitational force is just the mass times gravity, and so this is going to be 2mg, right? We also know that the floor is a surface that's going to apply a normal force, but no friction here because we know our problem is frictionless. And so we have our normal force from the floor, Fn, and we'll put our little superscript 2 here to remind ourselves that this is the force on the second block. And finally, we know that there is a tension force, right? That's our last contact force. And so let's draw a rightwards arrow to represent the tension here. And we'll call this T2. Or in other words, the tension force on the 2m block, right? Okay, cool. And so that's our 3 forces. So let's move on to the other block, the block of mass m. And so similarly, what I'm going to do is start by counting the number of contacts. And so I have my 1 floor contact. I have my rope pulling to the left, and I have the kind of applied force rope pulling to the right? So I've got my 3 contact forces and 1 non-contact force. So let's start with the non-contact force. This is going to be the gravitational force on the first block, which we can shortcut and write as just mg. We know we have a leftwards force from the rope on the left-hand side, this guy here, and so we can call that T1. We have our force from the rope pulling towards the right, and so we have this, and we'll call this the F applied. And we know that the floor is going to be applying an upwards force on M, right, since the surfaces are touching. So we have F1N. And so I want to point out, this is like a super not to scale free body diagram. Technically speaking, it doesn't have to be. It's sometimes beneficial if it is, but I'm just being a little bit lazy here. What's important is that our free body diagram is accurate to the forces that we need to represent in our Newton's second law equation, right? And so I'm pretty confident based on the number of forces that we expect that we've caught them all for our free body diagram. Okay, and so the next step is going to be writing out the Newton's second law equations, right? And so remember, the thing that you want to be really careful of when you write your Newton's second law equations is to be very, very literal and base it on the free body diagram, right? And so I'm going to start things off by just setting up the left-hand sides of all my equations. So we have F net x1, F net y1. And this is our first set of equations for the rightmost object, or the kind of block of just mass m. Then the other set of equations we need are for the left side blocks, which is F net x2 and F net y2, like this, right? Okay, so now what I need to do is go through each of my kind of Newton's second law equations and then figure out which forces belong with which equations. So this first equation represents the x direction for the block on the right-hand side, right? So that's this guy here. And it's going to be the horizontal forces. I can see here that I have 2 forces that have components in the horizontal direction. In fact, they're kind of fully in the horizontal direction here. And so my first force is going to be this rightwards applied force, Fa. And let's even track this in blue, just because we've written it in blue here on the right. And the other force I have is this tension force pointing to the left. So let's stick a minus sign to remind ourselves that this is left, and we'll call it T1. And because these are the only 2 forces in my free body diagram, they should be the only forces in my Newton's second law equation as well. And I can finish things off by writing that the total force tells me about the total acceleration a1x, or in other words, the horizontal acceleration of this first block. Okay, let's look at the y direction now for this same block, right? So here we have 2 forces. We have our normal force pointing upwards. So let's look at Fn1. Let's add Fn1 to our free body diagram, I should say. We also have the downwards force, the downwards gravitational force. And so we know that there's going to be a minus sign here because this thing points down, and it's just going to be value mg, right? And because I've exhausted all of the vectors in my free body diagram, this should be all I need to write in my Newton's second law equation. And so this thing had better tell me what the mass times the acceleration of the first block is, right? Okay, cool. And so let's go on to the other free body diagram, the one on the right, this guy. Oh, excuse me, the left for the second block, right? And so for the second block, I can see that there's only 1 force in the horizontal direction, which means it's really easy to translate this free body diagram in the x direction. All I have is this positive T2. And so that means that T2 just directly tells me what the mass times the acceleration is of this block. because this block has a mass of 2m, I'm going to shortcut a little bit and write 2m times a 2x, right? Where we've written a 2m here instead of m because the mass of the block, right, is twice as big as the first one. And then the other thing we have to do is the y direction for the left-hand side block. And so if we look at the y direction, right, we've got our normal force 2 in the upwards direction. So let's write a positive value here. And we also know that there is a downwards negative gravitational force, right? So we have our minus 2mg. And there's no other forces in the y direction, so we can safely write the right-hand side of our Newton's second law equation, 2m a y2, right? Okay, good. So some of you may be looking at these equations and saying, hey, you've like missed 1,000 simplifications you could make. And you're totally right. There's a bunch of simplification we could do at this point. But for those of you who are kind of struggling to do force problems, it may be tempting to start simplifying things as early as possible. I actually think that can be kind of detrimental. And really what you want to do is leave those for the third step, which is constraints. And we'll see here how that can be kind of beneficial for us. So remember, our constraints are basically things we know about the system, like mathematically, just based on the setup. So for example, in my opinion, the easiest ones to recognize right away are that the accelerations in the y direction of both of these blocks are both 0, right? These blocks are not accelerating upwards or downwards, like in these directions. So we know for a fact that there's no existing vertical acceleration here. And so this means that the right-hand sides of our y direction equations are much easier. Actually, let's leave it and let's just cross it out like that. Another constraint we can recognize comes from this massless string idea here, right? We know that for a massless string, if a massless string is applying a tension to two different things, then the tension has to be the same all throughout the entire string. We can't have different tensions on one side of the rope compared to the other. And so what that means is T2 and T1 have to be equal. So let's just call them capital T to make things a little bit easier. Our last constraint has to do with the fact that these things are tied together, right? So if the 2m block is accelerating to the right at some rate a, then we know that the right side block, this one here, also has to be accelerating at the same rate, right? We know that there's no slack in the string or anything like that. And so whatever acceleration a1x is, it has to be the same as a2x. And we have even more information. In fact, the problem tells us that this is the blue acceleration a, right? Our kind of given here. And so that's really nice because we've basically eliminated a bunch of variables using our constraints, and we can see how these are the simplifications that we were kind of looking for, right? So the first thing we can recognize is this guy here. Oh, we've already done that constraint, sorry. The other constraint we need to kind of input here is that the tensions are the same. So what I'm going to do to represent that is get rid of the subscripts because these are really the same tension, just capital T, right? And finally, because we know the accelerations in the x direction of both blocks are also the same, I can replace these two different unknowns with just a regular old blue a that we got from the problem, right? Because we know that the value of ax1 and ax2 are exactly the same. Okay, and so I'm going to do a little more simplification here. Technically speaking, you don't have to do this, but it's just a faster way to do the problem. We can recognize that all the interesting stuff happens in the horizontal direction, right? So in other words, the only equations that involve the acceleration and the applied force and the tension are these guys here. So it turns out you don't actually need to use the y direction equations at all here. Okay, so let's copy these equations over and see if we can solve them yet. So I'm going to start by copying the top equation for the first block. Fa minus t equals m times a, like this, right? Similarly, for the second block, I know that my equation reads t equals 2m times a. Okay, and what I'm going to do is use this little purple pen to circle all the unknowns that I have, right? So based on the problem, we know what the acceleration is. So this blue a is a known value, right? The problem also tells us what the masses are in terms of a variable, right? It's lowercase m, but we know that's a known value. And so the unknowns here are really the applied force that we were looking to solve for. And the only other variable here is the tension, which as of now is also unknown. Okay, cool. And so what that means is after these 3 steps, right, we've gotten a set of 2 equations with 2 variables, and technically that should be solvable, right? And so I'll label these equations A and B. And the first thing we can see is that equation B is very easy to solve for the tension, right? It just tells us that T equals 2ma. So equation B tells us T equals 2m times A. So what I'm going to do is substitute that into equation A, and now equation A will read Fa minus 2m times A, after plugging in the value for the tension, right, equals m times A. And so now if I add 2ma to both sides, I'm sorry, I didn't switch the pen colors, but I'm just lazy like that. We can find that the applied force, Fa, is simply 3m times A. Good. And so, just to do a tiny bit of sense making, because I cannot resist this urge, this makes a lot of sense, right? From the physics teacher's perspective, this is like you're just pulling a block of mass 3m to the right. And so you just need to basically apply enough force to pull both of these simultaneously, and it's going to basically weigh as much as if they were glued together. But kind of sense-making aside, right, I hope you can see why this process is really, really valuable when you're solving force problems. The first 2 steps, I think, are really nice and straightforward, and you can do them without knowing exactly which direction you're going when it comes to problem solving, right? We know that we can always construct a free body diagram for these, and we don't necessarily know what we're going to do with all the forces, or even which forces are like knowns or unknowns, right? But we can always make our free body diagrams. Then when we go from step 1 to step 2, right, we haven't done anything special. What we literally did was we looked at all the horizontal forces and the vertical forces in each of these, and we just like copy pasted them and did bookkeeping on them to figure out which ones were in the X and Y directions, along with kind of figuring out which direction the signs, or which signs we have to put in front of them based on the direction of the forces, right? So going from step 1 to step 2 is like also a pretty straightforward step, in my opinion. The difficulty with solving force problems, in my opinion, is also generally in step 3 when you're thinking about your constraints. This is honestly a little bit of an art as well as a science, and so you'll kind of have to get used to spotting these key terms. A lot of problems will have these like little nuggets of information that suggest things. So for example, a massless string is a really useful little nugget of info because that means that the tensions are the same, right? And so you'll kind of have to learn how to get used to translating each of these little pieces of information into a mathematical constraint. That's what I kind of refer to as like speaking physics, is you have to be able to use math to express these plain English ideas. And then finally, right, the upside of this process is if you've done steps 1, 2, and 3 correctly, in step 4, if the problem is like a sensical physics problem, you should just be able to solve, and the answer will just sort of algebraically fall out, right? If you find that you're missing some information, usually what that means is you're missing a constraint, and so you should go back and look and see if you've kind of missed a mathematical idea somewhere that the problem gives you a hint about. This is like the most robust method of solving force problems that I've stumbled upon in the last decade of tutoring or so. And so I'll challenge you all, I guess, to see if you can find a physics problem that this process doesn't let you solve. But thus far, I've not run into anything that can't be at least approached with this 4-step procedure. And so if you're having trouble setting up force problems, I really, really encourage you to try this out for a couple of them. And as you get kind of more familiar, this will go faster and faster. But this is a really nice systematic way of starting every force problem, in my opinion. All right, that's really all I have. I will end things on this slide here, just so you can see the kind of full glory of the 4-step process. As per usual, if you have any thoughts or questions, you can feel free to leave those in the comment section down below. Also, if you have any problems that you've been struggling with, especially force problems, right, and you want to see this process applied to maybe a more complicated problem that you're trying to figure out, you can also leave that in the comment section below, and I'll try to make like an office hours video where I work through that problem kind of in the framework of this 4-step process, just so you can see kind of how I might approach such a thing. Finally, don't forget to like and subscribe for more free physics problem solving tips. This has been Physics Tutoring Quantized.